In today's lecture, we will look at two more examples on how to use Ruth array to determine the range of the control parameters so that the closed loop system is stable. Here's the first example. We want to determine the range of K to make the closed loop system stable. We have an open loop system. Then we have a controller K, and the system is connected. The loop is closed by a unity feedback. Then let me first ask you this question. Let's look at the open loop system. Is this system stable, unstable, or marginally stable? The open loop, only this transfer function.
Would it be stable because it's always the power 3?
It's unstable because we have a pole. So 1 is in the right half of the S-plane. So the open loop system is unstable. If the transfer function has any pole in the right half of S-plane, then the system is not stable. So the open loop system is not stable. So if we only use a constant gain parameter, if we do not close the loop, then this controller will not change the pole of the transfer function. So if you use a controller in the open loop, you will never make an unstable system stable. Then we have to close the loop. Then we have to, when we close the loop, we have to determine what the range of the parameter K can make the closed loop system stable. That means the transfer function from the input to the output. So the first step, you need to calculate the transfer function from the input to the output for this closed loop system. Yeah, I will let you do it. If you still remember how to calculate the transfer function. So there will be the forward path gain over 1 minus the loop gain. Then you write the transfer function in the form of the ratio of two polynomials.
factor it out?
Yes. To use the root array, you need the coefficients. That's why you need to expand it, not factor it, expand it to get the coefficients of the polynomials. First, you need to find the transfer function. So the numerator will be the forward path gain. So k times s plus 1. Then s minus 1 and s plus 6. So the denominator will be 1 minus the loop gain. The loop gain will be minus k times the open loop transfer function. It will be plus k times open loop transfer function. Then you multiply s minus 1, s plus 6 on both numerator and denominator. We have s in the numerator, you have k s plus 1. Then the denominator, you have s minus 1, s plus 6, then plus k. Then to apply the root array, you need to know the coefficient.
Why?
Oh.
Why is it?
And here it's k s plus 1. Okay, sorry. K s plus 1. Yeah. You need to expand this polynomial, get all the coefficients. Then we can apply root theory. Yeah, you can time yourself. In your exams, you have to do some question like this. First, I find the transfer function, then the denominator polynomial.
This is part of the home. This is like we're doing the homework, right?
Yes. Yeah, roughly you have 10 minutes to finish questions like this. Have you got the denominator polynomials?
first row is 1, 5, 1, and the second row is 1, -6, 0.
You see? Do you have polynomial like this? The denominator polynomial?
I don't have, I did my algebra wrong. I have 6k, not k minus 6. But
Yes,
yeah.
it's k minus 6.
Yeah.
Yeah. Then you can write the root array. So the first row starts with 1, then second row 5, then k minus 6, then k. So what's this element?
Minus 6 minus k over 5.
Yeah, 5k minus 30 minus k would be 4k minus 30 over 5 and divide by 5. This times together minus k, 4k minus 30 over 5 divided by 5. So we can put 0 here. So what's this element?
Squared minus 3k.
Actually, it's very simple, just k. I think these two multiply together, then minus 0, then divide this term, it's just k.
Oh, yeah, you got divide.
Yeah.
Totally.
It's just k, okay? Because we have 0 here. So these two multiply together, then minus 0, then divide by this term, have k for the last element. Then what's the condition to make the closed loop system stable?
No negative term.
Yeah, no negative terms. All positive terms. No 0 terms. All positive. This means we need to make the system stable, we need to have k is greater than 0, 4k minus 30 is greater than 0. Then what's the range of k? 9? You can exactly calculate the k. Yeah, don't need to be an integer number. Yeah. What's exactly the range of the k to make the system stable?
Greater than something.
Yeah.
0 is 7.5. 7.5.
Yes, k. The first one you get k is greater than 7.5. Then you think if k is greater than 70.5, it's greater than 0. Yeah. So the only condition is k is greater than 7.5. So in this case, you see if you pick a controller, the gain of controller is some value greater than 7.5, you can make the closed loop system stable. We get the analytical bound for the parameter k. It will be very difficult if you use MATLAB to calculate. But when you assign any value to k, then you can use MATLAB to calculate the roots. Even though you pick k in this ring, greater than 17.5, to make the system stable, but different value of k may give you different response. If I assign k exactly at 7.5, then I can use MATLAB. You can use MATLAB to calculate the roots of the denominator polynomial. So we have the roots -5. It will be, if I draw the S-plane, it's the real part, imaginary part. One pole is -5. Then we have minus and plus 1.22. Then we have a pair of roots on the imaginary axis. The system is neutrally stable when k is 7.5. And here it shows the step response. If the input is a step signal, it's a unit step signal. Here it shows output. When k is 7.5, the output will oscillate because of a pair of complex roots. If we pick k is 13, then we can calculate it again. So in this case, we have different roots. It will be minus 4.06, a pair of complex roots in the left half of the S-plane. Then we know the system is stable because all the poles are in the left half of the S-plane. Then here it shows the response. This line shows the response when k is 13. If we pick k is 25, again we have one pole at minus 1.9 and a pair of complex roots. Because all the poles are in the left half of S-plane, the system is stable. This is step response. When you think of the performance, we want the output to track the input. Which one has the best performance?
How do we do?
You just think, okay? You want the output to be as close as possible to the input. That means tracking.
Higher K?
What?
The higher K?
Yes. So when k is 25, it's very close to the unit step signal. Here is the unit step signal. the input is 1. You want output to be as close as possible to the input. That is K is 25. So that's control design. You need to design a K first step to make the closed loop system stable. Then you can adjust the value of K to give you a desired performance.
Okay, so that's why we're determining the value of K to make the system stable?
First, yeah.
So, because it's already not stable, but by choosing the value of K, it's going to make it stable?
Yes. Then you can, within the range, you can pick the value of K.
And the word neutrally stable, that's the same as saying marginally.
Marginally stable, same. Yeah.
And you can't determine whether it's neutrally stable or not by just like looking at the transfer function?
You can. If all the poles are in the left half, but a pair of complex poles on the imaginary axis, not repeated. If they are repeated, it's unstable. If they're not repeated, it's neutrally stable. Now let's move to the next example. Here we have 2 parameters. Here's the open loop system. The same thing, we have a controller with 2 parameters. We want to first determine what the range of these 2 parameters to make the closed loop system stable. This controller is called PI controller, that we'll discuss later. So K is a P term, proportional, Ki integral. It's called PI controller. Now let's look at the open loop system. For this open loop system, is the system stable or not? Stable, yeah. In this case, the system is stable. But when you look at the step response, here is open loop step response. What's the tracking error in the steady state? The tracking error, what's the difference between the input and output when the T is very large? We have unit step input. Yes, 0.5. This is our input signal. The input signal should be here. It's 1. But this is the output. This is the step response. So output, eventually, the value is 0.5. So the error between the two is 0.5. So in this case, even though the open loop system is stable, but it cannot satisfy the performance, the tracking performance, then we need to design controller. But as I mentioned before, when you design the controller, if the parameters are not properly chosen, you can make a stable system unstable because of the feedback. Therefore, the first step, we still need to determine the range of the parameters to make the closed loop system stable. So same thing, first step, you need to find the transfer function for the closed loop system from the input to the output. Yeah, I will let you do it. Find the transfer function from the input to the output. What you need is a denominator polynomial. Did you find the denominator polynomial?
I think so.
Yes.
S cubed plus S squared plus 3S plus 2.
So here's the denominator polynomial. Then you can use the root array to find the conditions on K and Ki to make the closed loop system stable. Are you finished?
I don't know if it's right.
What's here? What's this element?
6 plus 3K minus Ki with 3.
Yes. What's here?
For that, I got long. I got 4Ki plus 3Ki.
Yeah, no. When you look at this term times this one minus 0 divided by this one, it's just Ki. See?
Yeah,
Just Ki.
Yeah,
Yeah.
maybe if I factored it out or like just algebra.
You see, here we have 0. This term times Ki, and divided by this term is just Ki. Then what are the conditions to make the closed loop system stable?
The negative term, all positive.
All positive. Yeah. You have 6 plus 3K minus Ki greater than 0, Ki greater than 0. it shows ki. We can pick ki first. Ki needs to be greater than 0. Then we can pick k. Then 3k plus 6 needs to be greater than ki. Then we know the closed loop system is stable. But this example shows the real advantage of root array. We get exactly the bound on ki and k. Then if you use MATLAB or numerical calculation, it's difficult to get the exact bond. Now I will show you how to get the exact bond. So we have ki greater than 0 and less than 3k plus 6. First, let's do the first part. The ki equals 0. If we draw the ki plane, so ki is equal 0 is the y-axis. That's ki is 0. For the region ki is greater than 0, is it left or right? Right, yeah, this part, all this part corresponds to the region ki is greater than 0. Then now let's look at the second part. How ki is equal 3k times 6. It's a line. Okay? We only need to find 2 points. First point we can find if k is 0, what's ki?
K is 0, K right, 6.
6, yeah, this point. This point is k is 0, ki is 6. So another point, the ki is 0. What's k? Negative 2, yeah. Have 2 points. Then we can connect the 2 points to get the line. Now I have 2 regions. Which region corresponds to ki less than 3k plus 6? Upper or lower? Upper. It's very easy to test. How to test? You can plug in this point. You can plug in any point. For example, 0, 0. If you plug in 0, 0, it becomes 6 is greater than 0. Then it's true. This means the point 0, 0 is in this region. Then we know it's in the upper part of this line. Then all the feasible k and ki will be the shaded area. That's exactly the bond. Then you take any points in the shaded area. It can make the system stable. Again, when you pick, even though you pick points in the shaded area, it can make the system stable. But the response can be quite different. First, let's use the proportional control only. Let the integral part be 0. That is, we let ki be 0. We only use the proportional control. And here it shows the step response. If the input signal is a step signal, this line shows the step response.
Oh, so KI, that's the integral. That's what that goes to? Okay.
Integral,
All right.
yeah.
All right, that's it.
Yeah. If we don't use the integral, okay, let's ki be 0.
Okay.
So in this case, you have to pay attention, okay? So in the denominator is not order of 3, it's order of 2. Here, if you let ki be 0, so the denominator polynomial is order of 2, not order of 3. Had 2 poles, 2 complex poles. Here it shows the step response. Here's the tracking error. Can you guess, can we reduce the tracking error by using different value of k?
That made it bigger, didn't it?
Yeah, you can make it bigger.
Are you asking if you can reduce it?
Yeah, can we reduce? Now you think this error is about larger than 0.6. So then in the open loop, it's 0.5. We make it worse. So can we adjust the k to make this error smaller? Yes, we can. Yeah, we can pick a larger k. So the k is large. This error will be small. We can pick k very, very large to be very close. But the tracking error will never be 0, no matter how large the k is.
What's our reference that we're trying to make the error be?
Oh, this is the unit step.
Just simply 1?
Yeah, still the unit step tracking problem. Yeah,
Okay. Unit step is our reference.
this is a reference. Then later we will learn how using the k alone, it's not possible to track, it's not possible to make the tracking error be 0, no matter how large the k is. We can make a very large k to reduce the tracking error, but this error will now be 0 if you use k alone, proportional control. Now let's pick a different value. We don't need to be very large value. Just k is 1, ki is 1. We're using pi controller. So in this case, it's very interesting. For in the numerator, we have s plus 1. Then in the denominator, we have s plus 1 power 3. So we have 1, 0. Here it's minus 1 and 3 poles at the same location. But in this case, the response of the system, we can cancel 1 s plus 2. It'll be the same. If you look at the response, you same with the transfer function 1 over s plus 1 squared. When you look at input output, this transfer function is the same with this transfer function. But this is only possible we have some minus 1 pole in the left. If any pole in the right, you cannot cancel it because it can make the system unstable. Here the step response. When k is 1, ki is 1. Last, let's pick k be 10, ki is 5. In this case, we have 1, 0. Minus 0.5. A pole here. Minus 0.46, then a pair of complex poles. Here it shows the step response. If I ask you, in this case, you think which response is the best?
K=5.
Yeah, this one could be the best, depends on from which point, which perspective. You think this one, its response is fast. Yeah, response very fast. But there is one downside we don't like. It's about this part. You think this part, because overshoot. If you think the elevator control, you want to go to the first floor, second floor, but then you go up too much. Yeah. Yeah, even though it's fast, can take you very fast. Maybe only 1 second. You see, 1 second from first floor to the second floor, but it's go up too much. Yeah.
The top floor, we hit the roof.
Yeah, that's why even though it goes down again, then up again. Yeah, it's like a roller coaster. That's why but this one is like smooth. Yeah, but it takes too long. It takes 5 seconds. Yeah. So our control design, later on we will learn how to tune the parameters K and the Ki to give you a desired step response. It'll be something like this. You need to be fast, then a little bit overshoot, not too much. Then settle down at the desired input signal. So that's the control design. But first step, you need to determine the range of K and Ki. Then search the parameters of K and Ki in the range to make the system stable. Any questions? So these are the types of questions you will need to do in your midterm exam or final exams. So I gave you some block diagram like this. Then you need to calculate the transfer function, more exactly the denominator of the transfer function. Then you can use the root array to find the range of K or Ki to make the closed loop system stable.
I have a question. You made a comment about doing this in MATLAB. Have you posted a video yet on how to do this in MATLAB?
This one you cannot do it in, you can do it in MATLAB, but you have to program it. It's not the easy way to do it.
Okay.
For example, you program the first row 2 elements, you use MATLAB symbolic toolbox. Then this is the second row, then you know which 2 elements they need to multiply together, then minus the multiplication, another 2 variables, then divide another one. But in general, you have some very easy case like here, order 3. Then the root table is not very long. Then for the stability part, you need to be very clear about the concepts. Here I give you some of the questions in last year's final exams. Is it true or false? So the first one is the roots of the denominator polynomial are zeros of the closed loop system. True or false?
Aren't roots and zeros the same thing?
No?
Because you can have a pole be a root.
Yeah, that's a pole. So that's the definition for the pole, not for the zero. The zero will be the roots of the numerator polynomial. Yeah. will be the numerator polynomial. The roots of the numerator polynomial called zeros.
Because you zero out the denominator, it's like.
So you see, this case we have 0. 0 will be the poles. Sorry, it will be the roots of the denominator polynomial. We call 0.
Poles are the denominator.
The pole.
This whole is like going to infinity. And the
Yeah.
zero is like going to zero. I got the last week.
So what's the second one? A neutrally stable system has poles with geometric axis, the imaginary axis.
True. I say it's true.
That's true. Yeah. But if I say it in this way, okay, if a system has poles on the imaginary axis, then the system is neutrally stable. Is it true or false?
Okay, but if it also has roots elsewhere, then it may not be neutral. Right?
Yes, yes. Maybe they have unstable poles, even though it has poles on the imaginary axis, but it also have unstable poles. Then the system is unstable.
Okay. That's right.
So the last one, the root stability criterion is a necessary and sufficient criterion for determining the stability of linear systems.
True.
That's true. Yeah.
That's true.
Yeah, that's true.
That's a big statement.
Yes, yes, yeah. But sometimes we even put linear time invariant systems. But in
What's
general,
totally true for LTI?
for LTI, it's true.
Okay.
But linear system is more, it also includes time varying. But in general, in this class, whenever we mention linear system, we refer to linear time invariant system. So it's a necessary and sufficient condition. Then you need to know the condition is the first column of the roots array must be positive. That's all. Let's see you next week.
All right. Thank you.